before we move on, let's first pick up what we left over last weekend. So last week we were talking about sequence-to-sequence models, and in the end we discussed ELMO, so which is a pre-trained recurrent neural language model. Okay, we found that if you use ELMO embeddings, you get much improved results on different NLP tasks compared with using GLOVE or skipgram. And when we finished, we didn't discuss one topic, which is how pre-training allows ELMO to give much improved results on different tasks. So this is called transfer learning, which is a term that refers to transferring knowledge from one task, maybe a general task, to other tasks. Okay, so for ELMO, we gain a lot of knowledge when we do language model pre-training. And then the neural parameters has some general knowledge that can be transferred into NLP tasks, okay, for parsing, for information retrieval, for information extraction, for generation, okay. So, and let's have some comments and discussions on transfer learning. We didn't do anything special, right, on the neural parameters. We just pre-trained, and then when we have a new task, we take the input, we feed that to the neural network, and we can improve our output. So this means that the neural parameters, they are quite powerful in terms of transferring knowledge from one task to another. If you think about our traditional, discrete features, which we discussed for several weeks, right? So we have to capture the task input and output in our feature representation. So which means if we want to transfer knowledge from these features from one task to another, it'll be a formidable task. So neural parameters, they are so general that we can allow the transfer of different knowledge between different tasks. Here I list a few, right? We can transfer syntactic knowledge to semantics. We can transfer knowledge from the news domain to social media. And we can transfer even knowledge from English-French translation to English-Uzbek language. So for all this transfer, we don't have we don't have to do the engineering on the feature definition level. We just rely on these neural parameters to do the knowledge transfer. And in fact, we have seen other examples of transfer learning. For example, when we have the same neural network and we connect it to different output layers, we are already transferring knowledge from one task to another. You remember in week 10, we discussed dependency parsing, right? For dependency parsing, we had unstructured dependency labels using that biafine output layer, and we have that dependency label prediction as a different subtask. So we actually already shared information in the encoder layers, right, between the dependency labeling and the dependency structure tasks. This is multitask learning. And you can imagine we can do multitask learning between different tasks. For example, we have this model structure at each output node, right? We can use the hidden for a token to predict maybe a language modeling output, the next token. And we can predict maybe a syntactic task, maybe the part of speech. And people have shown that this kind of multitask learning will benefit multiple tasks, okay, simultaneously. But people have found that you can be more flexible. Here I give you one example. So when you have a multi-layer BioSTM encoder, people have found different layers can encode different levels of information. For example, people found lower layers can encode more shallow syntactic information, while higher layers will encode deeper syntax. So when people try to do multitask learning between part-of-speech tagging and dependency parsing, people found that you can use the lower layer hidden to predict the part-of-speech labels, while you can use the higher layer hidden to predict dependency labels. Okay? So they're very flexible. And all this knowledge are shared in your uninterpretable neural parameters. I shouldn't say uninterpretable because at the end of this week, we will see there are methods to probe into the neural network, okay, which helps us to explain them. All right, so here is where we are now. So we are in week 13, 1 week before LLMs, and we discuss an important era of NLP, which is called the pre-training era. So the story all begins with Elmo, but then people found that you can do more smart things, okay, compared with Elmo. So we will first talk about how to pre-train a transformer architecture, and then we will see how to use this pre-trained transformer to solve different problems. Okay, and in the end, we will discuss work that tries to understand how all these things work and whether there are limitations to these things. So as a beginning, let's think about Elmo again. Okay, it's a pre-trained recurrent neural language model, and from where you can collect contextualized word embeddings. Okay, by encoding the whole sentence, you can collect information about each token under the sentential context. So Elmo uses an LSTM, okay, multi-layer RNN, to do the encoding. But it turns out that transformer can also serve as the foundation model, the language model. And as we learned last week, transformer is an encoder-decoder architecture. So can we use transformer to simulate or to replace Elmo? Okay, it turns out that we can. In fact, we can take out the decoder of transformer and build a recurrent neural model. And we can also take the encoder of transformer to build another language model, where we can take the encoder-decoder transformer architecture to build a language model. So all these architectures can be pre-trained. And we will discuss these models. So the first is called GPT. So the full term is generative pre-training. Okay? So you can also understand it as generative pre-trained transformer. So this is a model proposed by OpenAI. It's a decoder-only transformer architecture. So the modeling target is still a recurrent LM. Okay? So you predict a word based on its sentential history context, as shown here. And how do you do the modeling? Okay, so you use a transformer decoder to replace RNN, all right? So there's no encoder, but you can encode the start of the token, okay? Maybe a start of the sentence token, S, as the first input token. And you just do the transformer decoder layer after layer to predict one token after another, and that's a recurrent language model. And I lay out the equation representation, okay? As you can see, so every token is augmented with the position encoding. And you take KD transformer decoder layers where at each token location you just predict the output word, okay, using a single neuron. All right. So the only difference is that there is no cross-attention layer, okay? And you can denote the beginning and the end of the sentences using the special S token. Okay. So transformer has some engineering details. For example, it is subword-based model, and we use BPE, right, to cut words into subwords. And GPT is trained using a large data set called web text. So this data set is private to OpenAI, but it contains about 40 gigabytes of text. So that's a lot. So the model architecture is like this, okay? When you pre-train this GPT model, you can use it for solving NLP tasks, just like Elmo. You can take a sentence and feed that to GPT, and you get the pre-trained contextualized embeddings, and you augment an existing neural model using these embeddings. But GPT found that you can do something smarter. How do you do it? You don't just take out the contextualized embedding, but you take the whole GPT as the neural foundation model for doing NLP tasks. And you can fine-tune the whole GPT model during your task training. The idea is basically to replace the neural encoder we learned in week 8 and week 9 with GPT. Let's take classification for example. So when you have a sentence, you do the word embedding, and you feed the sentence into GPT, okay? And you know, the last token has a hidden layer. And you use the hidden representation of the last token, connecting it with a softmax neuron to predict the class label, okay? And then when you train this classifier, you just fine-tune not only your output layer, which is randomly initialized, but also the whole GPT, which is pre-trained. This is called fine-tuning. And conceptually, this is very different from using Elmo, because when you use Elmo, you don't fine-tune Elmo. You just take the contextualized embeddings, right, and use them. But for GPT, you treat the whole neural network, the whole transformer decoder, as the foundation of your text classifier. And you train the whole neural network, okay? So obviously, there are more pre-trained parameters to be tuned compared with simple word embeddings. But it turns out that it's also very effective. All right, so this is GPT. But it turns out that GPT has a limitation, which is every token, okay, when you compute its pre-trained embedding, it can look at only to the left. It can look only to the left because it's a decoder-only model. So every token encodes only the previous tokens. So how does Elmo solve this problem? It trained two RNN-LMs, right? One from left to right, one from right to left. Can you do that to GPT-2? Well, it's a little bit like an engineering hack. So then people found that actually you can pre-train a transformer encoder which already contains bidirectional information. But in order to do that, a recurrent language model cannot serve the purpose, right? Because the encoder needs a whole sentence inside, rather than predicting every word. So people found that there's another language model for this target. The language model suits encoding. And the language model is an extension to the skip-gram language model, just as recurrent language model is an extension to n-gram language model. Okay? So do you remember skip-gram model, which predict a word in the middle, right, using context from both directions? But these windows are limited to k words. Okay? We dig out a word in the center from a 2k plus 1 word window, and we predict the center word. So masked language model is like you have a full sentence now, okay, and you dig out some words, and then let's predict those words. For example, if the sentence is I went to the space for lunch, and you predict the word, you know, so this is somewhere you eat, okay? So many words make sense. And by doing that, our language model can make use of context both from the left and from the right. So from this idea, Google built the BERT model, bidirectional encoder representation from transformer. The model is basically a masked language model, okay? It can be trained over large data by just taking words from sentences and predicting them. The model architecture is just a standard transformer encoder. If you forgot it, it's a recap here. So you have a sentence, you mask some words from the sentence, okay? And then for the masked token, you just use 0, for example, as the word embedding. For the other words, you take the randomly initialized embedding, and you augment these from, with a position embedding, and you go through KE transformer encoders, layers, and then you predict the masked words, okay? And it's worth noting that we add a W0 to the sentence. It's a special token called CLS, just as S, okay? How do you mask? You randomly select 15% of the words from your training data, and you change them to mask, okay? But then people found that this causes a difference between the training scenario and the testing scenario, because when you train your model, every sentence contains some masked words. You can represent the sentence, okay? But during testing, there are no masks. So the testing sentences are not seen in training, which causes some problems. As you know, you have to generalize in nature. So that's not good. So one way to solve this problem, okay, is to take maybe 10% of the masked tokens and change them back to the original words, right? So the model will learn, okay, even if the input is not masked, I can still represent it in terms of predicting it. But then this causes another problem. The model can be lazy. Whenever it sees an input that is not masked, why don't I just directly copy it to the output? Okay? So it will not learn to work hard and represent this token. It will just learn to copy this token. To avoid that, we can take another 10% of the masked words, okay, and randomly change it to a different word. Okay, so the prediction is still the original word. So the neural network will see that, okay, cannot be lazy to just directly copy the input, because sometimes the input is a randomly changed word. So you still have to think about how to recover the original word. All right? So all in all, it's like 15% of the words are taken to be masked. Okay, but out of these, 80% are really masked. 10% are the original word, and 10% are a randomly selected word. So this is BERT. BERT has another task called next sentence prediction. So basically, when you train BERT, you train it with 2 sentences, a pair of sentences, rather than 1, okay? And you use a special token called SEP. Right? That's a You extend the vocabulary with a special token to separate the two sentences. Okay, and you can randomly sample two sentences that are not next to each other, or you can sample two sentences that are next to each other. Okay, and then you can take a new task as next sentence prediction. The basic idea is you feed two sentences into the language model and you predict whether they are next to each other. So this helps BERT to better learn context, inter-sentence context. How do you do that? Okay, so you can feed the sentence as I write in this slide into BERT. And you take the hidden state, okay, for the CLS token. You take it out. And then you do a binary classification. If the two sentences are next to each other, you predict 1. If they're not, you predict 0. Okay? And because this prediction will back propagate to the whole encoder network, the encoder will learn information about whether these two sentences are really next to each other. This is the basic idea of BERT. Okay, it's a masked language model. And some details in terms of the implementation. So the first is it uses something not completely BPE, okay? It's called word piece as the subtoken extractor. You can think about it as another way to replace BPE, okay? The full technical details are unfortunately private to Google. But the rough idea is, for BPE, we repeatedly take the most frequent byte pairs or subword pairs to make new subwords. So word piece changes this technology into something more like PMI, all right? You use the probability of a word bigram divided by the probabilities of the two words as the criteria of merging. This is the token extraction. And BERT is trained on a large corpus, including Wikipedia, and a book corpus dataset, which contains a lot of different books. Okay? They just merge the two corpora and use it as a data to train the masked language model. The model size is shown in this table. Okay? So BERT has a base version and has a large version. And they change the differences on the number of heads, number of layers, the hidden size, the size of the hidden vector. Okay, and all these combined together influences the number of parameters. So how do you use BERT? You take the same thinking as Elmo. As GPT, not the same as Elmo, okay? So for all the models we discussed this week, they're different from Elmo. So that's why Elmo lives in the last week, okay? So BERT is also fine-tuned. So I still take classification, for example. When you have a sentence, how do you build a text classifier? You just embed a sentence, or you just feed the sentence into BERT, because BERT has an embedding layer also. And BERT will find a representation. You take the hidden for the CLS token, right? And you connect that with a neuron, softmax neuron for classification. That's the model architecture. You can see that you just connect an output layer to BERT, right? And then when you train the model using the classifier data, you fine-tune the whole BERT parameters. That can be a large neural network. I will show you how to use BERT for different NLP tasks later, but just get the idea of fine-tuning. There is a famous alternative to BERT called Roberta. Okay? It has no scientific innovation in it, but it's better engineered than BERT. It has the same model architecture, but it's trained using more data. There's one difference worth mentioning, which is BERT does the masking by just like pre-processing the whole data set. Okay, so each training sentence will have a fixed set of mask tokens. But Roberta does a different strategy, takes a different strategy by dynamically doing the masking. So in each training epoch, right, when the sentence, before the sentence is fed into the language model, you randomly mask a few tokens. So over different training iterations, you see different maskings for the same sentence. So this is the first innovation. The second innovation is that Roberta found that next sentence prediction is not so useful. So Roberta removed this training objective. So it's a pure masked language model. Roberta also has a base version and a large version. So the statistics are shown in this table. So that is a decoder-only model and an encoder-only model. As I said, we could pre-train transformer by using the original transformer. So this is another famous model called BART. So bidirectional and autoregressive transformer. By the way, a lot of these pre-trained model names are from cartoon characters. When you read these papers, you will see what they look like. Okay. So BART uses the original transformer. Okay. But it has an encoder and a decoder. So how do we define a language model to collect information? So BART uses a model called denoise autoencoder. So first, what is an autoencoder? You might have learned that in your computer vision class, or you might not have seen it. So an autoencoder basically works by encoding something, whatever it is, or a picture, or a language, or whatever, into some representation, maybe a vector, okay? And it will recover the original image or sentence, okay, from this vector. So an autoencoder has an encoder and a decoder, which is, okay, similar to transformer. So what is a denoise autoencoder? So the denoise autoencoder says, okay, when you have the input, you don't feed the original input inside, but you try to corrupt the input by adding some noise to it, okay? So the decoder will recover the original input. So this is called denoise autoencoder. By doing this, you learn linguistic information for both components. And to formally specify that, I have the equation on the slide. So, okay, what's the model architecture? It's worth mentioning that BART uses the standard transformer, but it changes ReLU to GELU. We learned that last week. So what are the tasks for denoising, okay? So we first have to change the original thing to a noisy thing. And BART chooses 5 different tasks. The first task is just what BERT does. It masks several tokens from the input and then to create a noisy version. The second task is, okay, it's more, it's stronger. It's just like, I don't tell you which one are masked, but I just delete it, okay? I don't leave any blanks, and you still have to recover it. So the third is also stronger than masking. So rather than masking 1 token, I can mask 2 tokens, okay, leaving 1 mask. Or I can mask no token, leaving a mask here. So in the end, you have to recover maybe phi, nothing from a mask, or you recover a small phrase from the mask. Okay. Another task is sentence permutation, which is BART can take multiple sentences as the input, and you just permute the sentence order, okay, for the language model to to predict the original version. Or you can do a special permutation called rotation, okay? You just cut the document somewhere in the middle, okay? And you put the first half to the last. You change this order. So this is called permutation. Okay, these are the different noises. Okay, so all the different ways to introduce noise to BART. And BART is trained, okay, basically using the same tokenization method and the same data set as Roberta. And BART also has a base and a large version. So the model size and the configurations are shown in the table. All right. You can see that they are roughly all on the same level of sizes, right? The base size is about like 100 or so, a megabyte. And the large size is about like 300 or above megabytes. Oh, sorry, a million parameters, right? Okay. How do you use BART? All right, you can still use the same strategy as BERT. Okay, you take BART as the base model. When you have an input, you feed that to BART. But now you have an encoder and also a decoder. So you simultaneously feed the encoder and the decoder with your input sentence, and then you can take maybe the last token from the decoder and connect it to a softmax output neuron for classification. Or you can take the encoder hidden and the decoder hidden and concatenate them together before feeding that to a output layer. Then you can fine-tune the whole neural network. However, for BART, okay, you can also have a strategy which is to let it generate your output. You use BART as a sequence-to-sequence model. So this is particularly suitable for like sequence-to-sequence tasks, for text summarization, for example. We will see more examples later. Now we have introduced 3 typical ways to pre-train transformer. And we are ready to begin a new stage for NLP research. Okay, we can look at the NLP tasks from the pre-training perspective. We can use all these characters, cartoon characters, to solve NLP problems. And this new era is maybe termed as the pre-training and fine-tuning era. Okay, so the 2 steps are typically, you just take a pre-trained model as the basic model structure, and you connect it to some output layers to make a task solver. And then you have a set of supervised task data, and you tune the whole model. And you have a very strong performer. And students realize, okay, with that, NLP becomes very easy. We don't have to write thousands of lines of code to solve an NLP problem. We only need maybe 100 or 200 lines of code, okay, to get the state-of-the-art performance, which is maybe still more difficult than you, right? You only write 20 lines of prompt. So this is another story we'll think about next week, okay? Then I'll lead you through how people solve NLP tasks in classification, structured prediction, and generation, as I showed you earlier, right? But there are also other things to consider, okay? Beyond just what I described. And they're mostly focused on how you can fine-tune a pre-trained language model. I'll also show you those. Okay, so let's first look at text classification. The left picture is what we had in week 8 and week 9, okay? So it's a multi-layer neural network structure. When you have a sentence, you change the things into word embeddings, and you feed the word embeddings into a sequence encoder layer, and you have an aggregated hidden representation, and you feed that hidden to a softmax neuron. As I said, in the pre-training era, right, you can just replace the sequence encoder with BERT, Roberta, and their counterparts, right? And then you take the hidden for the CLS token. Why CLS token? Why don't I just do a pooling aggregation or attention aggregation? It turns out that CLS token is already an aggregation of all the other tokens. And the reason is simple. It's because the attention neural network calculates hidden by doing an aggregation over all the other tokens with position embedding, okay? However, that doesn't stop you, okay, from building another attention layer to aggregate BERT hidden for every token. You can do that. As I said, BERT encodes 2 sentences also, right, with this kind of representation. So you can use BERT to classify 2 texts also. We learned that 2 weeks ago, right? So we learned how to do natural language inference and paraphrase detection by concatenating 2 sentences together. Now you can feed this kind of concatenation to BERT and use the CLS token to predict whether the 2 sentences are entailment or contradiction or neutral for NLI, okay? Now let's look at another problem, which is word sense disambiguation. We didn't discuss this task throughout the past weeks, but we learned this task in week 1, okay? So it's a recap. The input is a sentence. Maybe he went to the bank and closed his account this morning, okay? And the task is to predict the meaning of bank, all right? So the reference dictionary can be some ontology or lexicon called WordNet or other lexicons, which contains different senses of the same word. And WordNet has a lot of senses for bank, okay? The river bank, the financial bank, etc. So word sense disambiguation is to match the sentence and the word, okay, with one of the senses in your lexicon. How do you do that? With BERT. All right, in the end, it turns out that you can use one BERT model to find the representation of the sentence, okay? And you can take the word bank out of the sentence. You use the hidden for the word bank. And then you take another BERT model, okay? So these 2 BERT models can be fine-tuned into 2 different sets of parameters, okay? You use another BERT model to encode the WordNet sense. It's also a sentence. And you take the CLS token hidden. Now you have 2 vectors. you just take the two vectors maybe and you use the distance measure. We learned that 2 weeks ago, right? You can use cosine or a neuron to calculate the similarity, all right? And when you do the output, you select the sense that has the most highest value of the similarity with the original sentence, bank hidden. Then you fine-tune the two BERT encoders to make sure that the correct sense matches the contextualized representation. Okay? When you do this, the BERT for the sense encoding will learn how to represent the senses, and the BERT for the input embedding will learn how to represent the word. It turns out that they can do the word sense disambiguation quite efficiently. Okay? So this is for classification. I used the 3 examples. Okay, take BERT, fine-tune it, and get good result. Take BERT, fine-tune it, get good result. And people found that it works for many, almost most of the NLP tasks. And then people found another problem, which is your BERT is very general. It's trained on Wikipedia and book corpus. But my task can be very specific, okay? Maybe biomedical text, or scientific text, or computer text, okay? So there's a mismatch. I can do the fine-tuning, but maybe I can do it better. Can I adapt knowledge from the BERT better to my test domain? And how to do that? So continued pre-training is a strategy, okay? So the idea is you have a pre-training and the fine-tuning step. Let's insert something in the middle. It's called continued pre-training. Now, suppose your test data is from the biomedical domain. You can just collect a lot of biomedical text without any annotation, okay? And you use the same mask language model as the training objective. And you continue to pre-train BERT, or you tune BERT on the language model objective over your biomedical data. In the end, your BERT will contain your domain knowledge in addition to general knowledge. And then you just do the fine-tuning as before, okay? So this works not only for classification, but also for other tasks using BERT. A second problem is, well, you can fine-tune BERT here and fine-tune BERT there. But fine-tuning BERT can be more costly because the model is large, okay? So how can you do parameter-efficient fine-tuning? Or how can I fine-tune a model, okay, without fine-tuning all its parameters and get similar results to fine-tuning the whole model? So one way to achieve that is called adapter. Okay, what is adapter? So adapter is to add a set of additional parameters to a pre-trained transformer model. So when you fine-tune the model, you don't fine-tune the pre-trained parameters, but you only fine-tune the adapter parameters. Okay? And then the whole model, including the pre-trained BERT or GPT or BART and the adapter parameters, as a whole, will serve the same purpose as fine-tuned language model. Okay, and your adapter parameters can be much smaller, maybe only 1% of the original number of BERT parameters. All right, So I show you one picture here. You know, we can use the transformer encoder to pre-train BERT. And each encoder layer has two sublayers. So multi-head attention and feed-forward network. You can add another MLP, okay, at the end of each sublayer, as I show you in this picture. And this MLP can be randomly initialized. And its structure is shown in the picture on the right, okay? It can be the connection of two matrices. One matrix is a dimension reduction matrix, okay? It has less columns and more rows, okay? So when it is multiplied with the input column vector, it reduces the dimensionality. The second vector is a dimensionality increasing matrix. It has less columns and more rows. Right? So when you multiply this matrix with the small hidden vector in the middle, you recover the original dimensionality. And when you combine these two matrices together, okay, you use a smaller amount of parameters to achieve the goal of having a multi-layer MLP, okay, multi-layer perceptron. Actually, we've seen this technology of dimensionality reduction and recovery, right? In hierarchical softmax in week 8, when you build the n-gram language model. Right, this allows you to use fewer parameters to achieve an MLP. But this is not the only strategy to add an adapter to a pre-trained language model. This strategy is called residual adapter. And the equation form is like this, okay? So originally, you have H in and H out for any pre-trained layer. So you augment H out by adding an adapter layer, okay, and produce H output adapt, all right? So this adapter layer is a two-layer perceptron. And the first layer is a dimension reduction layer, which reduces DH to DR. DR is much smaller than DH. And the second layer, W prime, is a dimensionality increasing layer, okay? It recovers DH, okay? So the larger DR is, you know, the larger the number of parameters in your adapter. You can control that. But even, okay, so this is like a cascaded way of adding adapter, right? You have a more parallel way or a simpler way of adding adapter, which is to change the original parameter matrix. This is called low-rank adapter, or LoRa. Suppose, okay, in your original transformer, you do the QKV mapping. Okay, you project original input into query key value in your multi-head attention. These are matrices. And also you can suppose that in your MLP, right, the feed-forward neural network sub-layer, you also have a lot of matrices, two matrices with a ReLU in between. So for all these matrices, you can add an adapter to them. So changing W to delta W. You can achieve this delta W by doing this dimensionality reduction and recovery. Okay, so this delta W is achieved by multiplying W prime prime with W prime, okay, which are two matrices similar to what we saw earlier. Okay, and when you fine-tune the pre-trained model, you only tune this delta W, keeping the original pre-trained W unchanged. All right, so this is the second way to change adapter. All right, but you can also add adapters to the attention layer. Both the residual adapter and the low-rank adapter are added to sublayers or matrices. You can change the attention function structure also. And you can change it in multiple ways. Here I show you two ways. Okay? So one way is you change the original attention function unchanged. Okay? So the attention is still softmax of K transpose Q. Okay? But you add another adapter function. So, and you add the two results together. It's more like a parallel version of attention, okay? And inside this adapter version, you can see that I still do some dimensionality reduction and dimensionality recovery using W and W prime, okay? So you tune this W and W prime parameters as a few addition. So the second way to add adapter to attention is to go inside, okay? You just directly change the scoring function, the attention weight function, by saying in addition to K transpose Q, okay, I add another adapter to calculate the attention scores. I call it attention QK, okay? And this can be done by having a multi-layer perceptron over the concatenation of Q and K at each position. All right, all in all, in summary, all right, the definition of adapter can be very flexible. In addition to the 4 adapters I showed you, you can define your own. And I'll show you one more example later. The advantage is that you can fine-tune only a small proportion of model parameters compared to fine-tuning the whole model, so which is more parameter efficient. And in addition, adapters are modular in the sense that you get the pre-trained language model intact without changing it. So every model parameter is still the same as after pre-training, okay? All you change are the new model parameters. So it's more modularized. But adapters are, during adapter training, you still have to do the feed-forward computation, which means that although the number of tuned parameters are fewer, of course the number of active parameters are still there, are still the same as before. And when you calculate gradients, you still have to make use of the original BERT parameters. So this is adapter. One more parameter efficient tuning method is called prefix tuning. So this can be seen as an alternative to adapter. So again, we introduce a few additional parameters, but they don't change the model architecture. They are a few prefix tokens before you feed the sentence into a pre-trained model, okay? So formally, these tokens can be represented as xp1, xp2, until xpn, okay? So the number of prefix tokens can be defined by yourself. These are embedding vectors which are fine-tuned during model tuning. In addition to these prefix labels, the remaining of the process is exactly the same as before, okay? So you embed the whole input sentence and you concatenate the token embeddings with a sequence of prefix embeddings, and you fit that to BERT or other pre-trained models. And during model tuning, okay, you fix all the pre-trained parameters, but tune only these prefix tokens. In other words, XP1 until XPN. So this also serves as a lightweight tuning strategy. It's more elegant because you don't even change the model structure. And it turns out to be effective for many tasks. Okay, so these are all parameter efficient tuning, but it doesn't change the testing efficiency or inference efficiency. There's another strategy, okay, which is to teach a smaller model, okay, to do the same tasks using the original large model as the teacher. This is called knowledge distillation. So, in other words, during inference, I want to use a faster model, a smaller model, and I want to approximate the accuracy of the large model. How can you do that? Okay, you use the large model as a teacher which already has a lot of knowledge, okay? And you try to distill all the knowledge of the teacher into the smaller model, the student. And in the end, this kind of knowledge distillation can well approximate what the teacher knows. And how do you do the distillation? You can set a few additional learning objective functions in addition to the original language modeling objective function, okay? So one objective, okay, is to make sure that the student has a similar token level distribution, okay, as the teacher in language model training. How do you make sure they are similar? We learned, okay, in week 6, all right? You have the KL divergence or Jensen-Shannon divergence to measure the difference between two distributions. And we can take that and minimize the KL, okay, between the teacher and student when you predict every token in master language modeling or during next token prediction in recurrent language models. So the student will learn, okay, what is the probability distribution of the new token, okay, by learning from the teacher. A second learning objective is to say, okay, not only the output distribution, but every hidden, I want to mimic the teacher on every hidden vector. Now, how do you measure the distance between the teacher hidden vector and the student hidden vector? Okay, you can use the mean square error loss, which is not a loss we talked about in my NLP class, but it must be a loss function you learn somewhere. Maybe in machine learning, maybe in computer vision, okay? So it measures the distance between two continuous vectors, like what I show you here, okay? It just use the difference and take the norm squared, okay? And you minimize that. You can make sure that the hidden of the student is also similar to the hidden of the teacher, okay? But this is applicable only when the dimensionalities are similar, are the same, okay? And then when you have the final loss function, you can take the original language modeling objective and the two additional objectives. You have some hyperparameters to balance the three, okay? So this is called knowledge distillation. But there are also alternative ways to do knowledge distillation. One very brute force way is to just use the teacher to generate a lot of data. And you train the student on this data. This also helps the student learn the teacher distribution, okay? I didn't include that in my slides, but that is useful for training generative models. Now, the second set of tasks. It's called structured prediction tasks. And when you use pre-trained models to solve these tasks, the idea can be similar to text classification. Okay, in week 10, right, we learned structured prediction. It's very similar to classification. You have the sentence, you change that to embeddings, you feed that to sequence encoder, and you add structured output layers. Now, all you need to do is to replace the sequence encoder with a pre-trained language model, maybe Roberta, okay? And the output layers can remain. For parsing, for part of speech tagging, for all the other tasks, you can just directly do the change. And here I just use one more example, okay, which is event extraction. I didn't discuss that with you in the previous weeks. You know, an event is just a composition of triggers and arguments. In this case, Jason visited Byte Dance. The event is a visit event, okay? The event trigger is visited, the word. And the event, it has some visitors and has something to be visited, etc. So we want to get that structure. How do you do that? We can perform the task in several steps. The first step is to identify the trigger word. Okay, and that can be done by a token-wise classification. We encode the whole sentence using Roberta, and then we ask every token, are you the trigger? Are you the trigger? Are you the trigger? Okay. So, visited is the trigger. It has an output 1 in binary classification. And then we perform the second task called trigger classification. Okay. Okay, good. You are the trigger. So what type of event do you represent? Do you represent a visit? Do you represent an attack? Do you represent a move, etc.? All different kinds of event. I classify it. Okay, this is a visit event. Now with that event, okay, the next thing to classify is, okay, who are the argument and what are the relations between the argument and the trigger? Okay, given that this is a visit event, I know the event has several arguments, the visitor, the visitee, okay, the time, etc. So for this event, I just use BERT again, okay, and I just ask every token, taken the hidden of the token, and maybe I combine this hidden with the hidden of the trigger, visited, okay. I add them together, concatenate them together, and do the classification. Are you an argument? Okay. What kind of argument are you? Etc. So after these few steps, I have the whole event structure. I can do supervised learning to tune BERT, okay, to perform all these tasks. All right. And the next thing I discuss is how to better inject knowledge into BERT for structured prediction. Let's revisit machine reading comprehension. The task is to find the answer for a question in a passage by identifying the answer span in a passage, okay? Which is a structure, just like named entity. And when you use BERT to solve the task, you can take the passage as the first sentence, you can take the question as the second sentence, and you feed them together into BERT. And then you just directly add classification output layers to ask every word, are you the beginning of the answer span? Okay, are you the end of the answer span? Okay, to do this kind of classification. Or you can add some more classification layers as what we discussed several weeks ago, making the prediction of the end dependent on the prediction of the beginning. All right. But here, we can have a better way to allow BERT to predict a span. So this method is called span BERT. The idea is we can add a span prediction as a pre-training objective function to distill span information into BERT. Okay? And how do we do that? We can mask whole spans and then ask the pre-trained language model to predict the masked span continuously. And when we predict the masked span, we use the neighbor words, okay, the two neighbor words of the span, as the source of information. In this picture, the yellow words, the yellow tokens are masked span. The blue tokens are the neighbors we use for predicting the span. Okay? When you predict the span, you predict each token in the span. By having the blue tokens as the input and having the relative position of the word in the span as the input too. For example, in this case, we predict the third word, okay, in the span. So we use the two blue token hiddens plus the position encoding for 3 as the input, and we predict the word football. Okay, so this is a span-based objective function. And when we train this objective function, we can randomly sample spans from a large amount of data, maybe reading comprehension data. Okay, no matter whether this span is a named entity or not, or it doesn't represent any meaningful thing. We just randomly sample the span and do the prediction. And this turns out to improve not only the reading comprehension task, but also span prediction tasks in NLP. Next, let's look at another interesting structure prediction task called table QA. What is table QA? So this is even a little bit in the bridge between NLP and database. So you have a question, you have a database table, okay? In this case, the database table contains a lot of student information. And suppose that a student is named Yue Zhang, okay? And he is from class 1A, and his student ID is 2023-0101, okay? And then the question is, which class is Yue Zhang from, okay? You know, when you do the task, you have many different solutions. So one thing is you first do the question to SQL task, right? Semantic parsing. So change the question into SQL and feed the SQL into the database, you get the class. But here, we want to use BERT to solve the task. How do we do that? We can represent each database row as a sentence, you know, as I show you here. And we can represent every database column also as a sentence. Then I can use a BERT model, okay, to represent the row sentence and the column sentence. And of course, we can use BERT to represent the question. Now the question and the row can form a pair, a sentence pair. We feed the sentence pair into BERT and use the CLS token hidden to calculate a score by adding maybe a regression neuron. sigmoid neuron to calculate a score. Similarly, we can feed a column sentence and the question sentence as a sentence pair to BERT and calculate a score. For testing, okay, I just choose the highest scored row and the highest scored column, you know, and the cell in there is our answer. For training, we just make sure that correct row and the correct column are scored higher than any row and any column. So this is table QA. Okay, I've been talking about BERT all the time, okay? How about BART or GPT? There are some structured prediction tasks, okay, that can be solved by making use of generation. The clever thing is we can map the task into some formats that are close to the sentence prediction objective. Now let's take named entity recognition, for example, okay? So he went to Beijing for a job interview is input. Now, originally the output is a span, right? I have to recognize Beijing and tag it as location. So this is named entity recognition. But can we do a generation task to predict Beijing as a location? Well, this task can be transformed into a template. Okay? I showed you the template here. There is a slot to fill, which is an entity slot. There is a slot to fill, which is the type of the entity, location. Okay? And with that, we can create a sentence. Entity is a type entity. Okay, as I show you in the slide. And then when you generate the sentence, you force, okay, the model to fill the entity span and to fill the type span. Okay, maybe you restrict the type to only a few words. You restrict the entity into only a span in the input. I can create different templates to do the same thing. And I can compare the performances of different templates. But whenever I have a template, I can fill the original input sentence to BART encoder. And I do something like force decoding, okay, template force decoding in a decoder. And I map the encoder to the decoder output to generate the sentence, Beijing is a location entity. Then I fine-tune BART using this generation task. It turns out to work surprisingly well, okay? Other structured prediction tasks can be done similarly. Again, now this is an event prediction task, okay? Suppose that we have already recognized the trigger, as I show you here in yellow, okay? Now we recognize the event type of the trigger, okay? And we can create a template, as I show you here in green. The template is basically a sentence that describes the event with the event type, the trigger, and all the arguments, okay? I mask the trigger and the argument as the things to fill in this template, all right? And I force BART to take the input sentence or passage and predict the template with the filled slots. What if a slot is not represented in the input? I just fill that with, okay, empty or none, right? For everything that is already represented in the input, I fill that with the input. And it turns out that if you tune BART in this way, it performs very well. This is structured prediction. For generation, the task is even simpler. I showed you for summarization, you can just feed the original sentence as input and use BART to generate the abstract. Here, let's consider a more challenging task. Open question answering. Okay, what is it? The input is a question, okay, and the whole internet, or a set of documents you want to use to answer the input question, okay? And the output is the answer to the question. It's more complicated than machine reading comprehension because there are multiple or a lot of candidate passages you need to read to get the answer. And how do you solve the problem? Okay, you can use the question as a query, okay? And maybe feed the query to Google, right? And Google will return you a few documents. You can take the top ranking documents, which are candidates, which likely contain the answer. So you concatenate each candidate passage with the question to form question document pairs. You know, when you have each question document pair, you can use BART. Question and document in, answer out. That's the basic idea. And you can also concatenate all the question passage pairs into a long input sequence. And then you train BART to predict the answer. So this is the basic idea of open question answering, okay? There are many improvements you can do on this basic structure. One thing that's worth mentioning is dense passage retrieval, DPR, okay? DPR uses BERT to find the most relevant passage according to the question. Similar to word sense disambiguation, we represent the question using BERT, and we represent the passage using BERT, okay? We take the CLS representations of the two, and we calculate the distance. Now, given many passages, we retrieve the closest passages as the answer, as the retrieved documents. So this is called dense passage retrieval. And of course, we need to fine-tune the two BERTs in order to find the most relevant passages. And the fine-tuning objective is to make sure that relevant passages are scored higher than irrelevant passages. Okay? How do you define this objective function? We can treat that as a softmax function, actually. And this is called contrastive learning. In the softmax function, the score of the relevant document is on the numerator. And the scores of both the relevant passage and the irrelevant passages are on the denominator. Okay? So in the end, you can think about all these scores, all these passages as class labels, and you have a softmax function over their scores as the objective function. This is called contrastive learning. Okay. So there are many other alternatives to do better open question answering, better passage retrieval, fine-grained passage ranking, etc. And you can read relevant papers given my introduction. Okay, we learned QA from tables. We learned QA from passages. And in week 1, I also discussed with you knowledge graphs. You can also do QA over knowledge graphs. Okay, here I show you an example. The knowledge graph contains a name, a person, Yue Zhang, contains a university, Westlake University, contains a city, Hangzhou, contains some professions, professor. And you know there are a lot of relations between these entities, which is a graph structure. Okay? Now, all we want to do is to answer any questions using the graph structure, such as where is Westlake University? Okay. So, you want to sort of solve two problems. The first problem is how you can represent a knowledge graph. The second problem is how you can integrate information from a knowledge graph with information from a question. Let's look at the two. The first is how to represent a knowledge graph, okay? Using the knowledge graph information, you can create a lot of tasks, okay? And one simple task is to say, how about we can predict one entity using another entity and the link. So the idea can be translated into a formula, which is you have an embedding of every entity, okay, a vector E, and you have embedding of every relation, a vector R, okay. If you want to predict the second entity using the first entity and the relation, a simple method is to make sure that the sum of the embedding of E1 and the relation embedding roughly equals to the embedding of E2. Okay? So the sum of Westlake University and the located in roughly equals to Hangzhou. Okay? So this can be a simple objective, right? To inject knowledge into these embeddings. And you can have an objective function like this. So the distance between correct samples, E plus R, okay, E1 plus R and E2. So this is like E1 plus R minus E2. So this is the distance. The distance of correct examples must be smaller than the distance of incorrect examples. Okay? I leave you the details for further reading. But there is one way to improve this objective. Okay? People found that this is too coarse-grained. The objective function cannot be effectively minimized. So we can do better. People realize that each entity, okay, under different relation can have different embedding representations. So we can add a projection matrix called W. The matrix is sensitive to the relation R, okay, WR. Now given two entities, E1 and E2, I first map the entity embedding E1 and E2 using this matrix WR into a relation-specific representation of the node. Then I do the same objective, okay? I use the embedding of E1 plus R to predict the embedding of E2. So a projection of E1 plus R is equal to the projection of E2. All right, there are, of course, many alternatives, and I don't have to introduce them in one class. Now, suppose you have pre-trained the knowledge graph so that every node and every relation has an embedding. I can represent the graph now. How do I do the question to graph matching? Okay. Now we can do a mapping between a question and a representation vector by feeding the question to BERT and get a hidden for the CLS token. Okay, now question into a vector. And from the knowledge graph, okay, I can find the embeddings of all the triplets. So now suppose the question is, where is Westlake University? I know the question. I have a hidden for the question. And I know a first entity, which is Westlake University. I can find this entity in the knowledge graph. Let's say it's E1, okay? And now using this E1, I can find its neighbors. Okay, every node connected to Westlake University. Maybe Westlake University located in somewhere. Westlake University, the category is an institution. And Westlake University, etc., are related to Zhejiang University, etc., etc. So I take everything, E1, R1, E2, E1, R2, E3, E2 prime, etc., etc. Now the task becomes, okay, from all these neighbors, find a neighbor, R and E2, that answers the question. Okay? Now the E2 I want to find is Hangzhou, and R is located in. Now I don't change the knowledge graph embedding. In other words, all these neighbor candidate embeddings are already pre-trained. What I want to do is to fine-tune the question embedding, HQ, okay? So that HQ is close to the relation located in. All right? And then if HQ is close to related in, then I can use the distance between every R, the neighbor of every R, to select the closest to the question. And the E2 that corresponds to that R is the answer. All right? Okay, given this problem formulation, which is innovative, all I need to do is to fine-tune BERT when I have a lot of gold standard question-answer pairs. We can make use of the knowledge graph to answer questions. Okay, we've seen a lot of creative ways to use BERT. Now, about machine translation. In theory, machine translation is very easy to solve, right? So you just take BART and fine-tune it. The input is the source, the output is the target, you are done. But unfortunately, you can't do that because BART is monolingual. So in order to solve the problem, people trained a model called MBART, multilingual BART. Okay, so they collected a lot of sentences from different languages. And they used a special embedding tokenization method, okay, called unigram tokenization, which is again an alternative to BPE and WordPiece. You can read it offline. And when you merge multilingual data, you can train a BART model by using a similar strategy, okay, but you have to add some additional tokens such as language ID to differentiate different languages, okay. Now with MBART, you can train machine translators. Of course, you can train structured prediction models as generation models by changing structures into sequences. And in this example, I showed you an AMR graph. you can actually sequentialize or serialize the AMR graph into some like bracketed structure sequence. And then you can tune BART to translate a sequence into a graph sequence or vice versa. Okay, so this is called AMR parsing or AMR to text generation. The interesting thing is you can also add a graph neural network on top of the BART encoder to better represent the structure. Okay, I only tell you the intuition. Moreover, you can design some masked language model or denoising tasks also on the graph sequence as continued pre-training data to improve the result. Okay? But let's leave the last few minutes for today into analyzing the structure of pre-trained language model. How does pre-trained model work? Why does it help so many different tasks? Now, people can't help probing into the knowledge inside pre-trained language models. And this line of research is also referred to as BERTology. So people try to understand BERT. A very seminal work simply analyzes the attention patterns, okay, over each attention head in each layer. So people just visualize, okay, what does every word look at in each attention function? And they quantitatively realize, okay, there are some syntactic heads, okay, this word, look at its dependent words, subject-object. There are some semantic heads, okay, which seem to be taking the predicate argument structure. And there are also some heads we can't interpret. So these are noisy heads, okay? So this is one way to analyze BERT, analyze attention patterns. A second way to analyze BERT is to say, okay, let's freeze BERT and add an output adapter, you know. This adapter is just a structured prediction output layer to predict like syntactic structure or semantic structure. So if I freeze BERT and only tune the output layers, and we can achieve high accuracies, then it means that BERT itself contains syntactic information, right? Because I'm using the representation as input, I only tune the output layer. So this is called probing. And people have probed BERT for parts of speech, okay? So this is one paper. And they find, okay, if I only tune the sequence labeling output layer, the part of speech accuracy is high, so BERT contains part of speech information. So how about we also probe into dependency layers, okay? They probed into both Elmo and BERT. So above, the black lines are the gold standard dependency parse tree. And below the colored structure is the output layer fine-tuned to predict a dependency tree. You can qualitatively find that the accuracies are really high, right? So which means the BERT hidden layers contain strong information about syntax. And then there are other people who say, why don't we just roll up our sleeves and predict everything, semantic roles, syntax, semantics, etc. And they find, okay, the accuracies are all rather high, okay? So, and then they say, okay, the reason BERT works is because it contains syntax knowledge, semantic knowledge, etc. How about lexicosyntactic knowledge? People also try to visualize BERT, and they find that across different languages, across different tasks, the hidden vectors form specific patterns. But you know, syntax and semantics are not everything we need to solve different tasks, right? Maybe these language models also contain world knowledge. And maybe they can do more. So people also try to probe, like, are there world knowledge in BERT? Like if I say, Dante was born in where? Okay, so if bird can predict like where Dante was born, then bird contains like Wikipedia knowledge, right? In theory, it could contain that. So the idea is to map a knowledge graph triplet, okay, entity, relation, entity, into a sentence. And then you mask one entity and let BERT predict that entity. And people found that like Elmo and BERT contains the correct answer, like Florence, to a high degree of accuracy. And you can also do one crazy thing, crazy at that time, okay? For open domain QA, we just don't use Google. We just use the language model itself, okay? Question in, answer out, okay? So when did World War II end? Okay, what's the question? And the answer is maybe 1945, some date. Okay, and we fine-tune a BART with some questions. And we look at, can BART answer other questions? And people found that a pre-trained language model similar to BART actually can answer those. And they are very excited. Okay. In addition to world knowledge, there are also common sense knowledges. Okay? For example, humans have legs. Okay? Or humans cannot fly. Okay? Or tables are in rooms. These are common sense knowledge. There are also knowledge graphs on common sense knowledge, such as the concept net. Okay? It contains a lot of common sense knowledge. And people can devise like similar objective functions as you probe into bird world knowledge to probe into common sense knowledge. And people found that pre-trained language models also have certain common sense knowledge. And you can also probe into common sense between two sentences, okay? Using tasks such as natural language inference, which I don't have time to elaborate. But people found that these pre-trained models contain some knowledge, but limited. And also, beyond knowledge, you know, when we humans solve tasks, we sometimes also reason, you know, right? Given that, given a premise, given some condition, we can reason and arrive at a conclusion, you know. So, when you're given some examples, they ask a language model to provide a proof or do deductive reasoning. Or they ask a language model to do multi-choice question answering tasks to see how much reasoning capability a language model has. And here, they found some challenge in pre-trained language models, okay? Although they contain a certain degree of knowledge, syntax and semantics, they don't do reasoning very well. Actually, they do reasoning very badly. Okay. So people also found some flaws in language models. I tell you one interesting flaw. Okay. It's like that. Language model perform natural language inference very well. You know, you have a premise, you have a hypothesis, you predict whether the premise entails a hypothesis. One day, people suddenly found, I only need to feed the hypothesis into BERT. I can still predict whether the premise contains the hypothesis very well. Oh, then there must be a problem. Because BERT don't even have to look at the premise. And you can do the work very well. It means it must be using some spurious patterns or patterns that are not the real rationale, okay, to answer the question. What are these spurious patterns? And people start to study the correlation between the premise or hypothesis with the answers. And they found that the data contains a lot of phrases, okay, that are statistically highly correlated with certain answers. For example, entailment answer, right, often contains like people, or the contradiction answers often contains the word not. Okay, so BERT learns, okay, whenever you see not, you predict contradiction without looking at the passage at all. Okay, so these are called shortcuts. So language models are not good students. They are bad students. They just look at shortcuts to answer questions. Here, people also study shortcut in question answering. You know, whenever you ask when for reading comprehension, the student doesn't have to look to answer to really understand the passage. They just find, okay, where is the time phrase? Whenever you ask when, I just find the time as the answer. And I can answer the questions correctly. These, again, are shortcuts. And then so people, including us, we start to look at, okay, does language models really contain world knowledge? Okay, we can look at, okay, if you train the model with when does World War II end, right? You train the question. And then you test the model on other questions. The models can also answer other questions correctly. But if you really carefully look at your test set, you'll find that a lot of the test questions have overlaps with the training questions. Okay? Maybe the question is a rephrase, paraphrase to the training question. Or maybe an answer is exactly the same as a training answer. So these overlaps occupy a large proportion of the questions that the model answered correctly, which leads to people wondering, okay, are the models really do the correct reasoning? You know, the rationale is the reasoning path people use. And the shortcut or spurious features are a path that the model uses, okay, which is not correct. They don't overlap. For sentiment, as another example, when we look at the word excellent, good, we predict positive label. But for movie review, the model might look at some other words that are correlated with good movies, maybe Nolan. Okay, so this is called a spurious feature. If the model overly relies on spurious features, it cannot generalize to other domains. For example, restaurant. Nolan doesn't represent a good restaurant. So here, there are studies on how pre-trained language models generalize across different domains. And people found that this out of distribution or cross-domain generalization is also weak for language models. And people also do adversarial tests on language models. For example, if we do machine reading comprehension, we try to add an irrelevant sentence to the passage. Whether your model can answer the same question correctly indicates how robust your model is. Or for natural language inference, right? You add a negation to the hypothesis or premise. You check whether the model can still answer the question correctly. It can evaluate whether the model uses rationale or takes shortcut. So this kind of adversarial tests or robustness tests were also interesting to a lot of researchers. With that, I finished this week, okay? So this is basically a period of time when people use models such as BERT and BART and GPT to solve all different kind of NLP tasks. People had excitement, okay? They try to analyze how this model work, and people have disappointments, finding that models take shortcuts and are not robust across domains, or they don't reason like humans, okay? So from next week onward, we discuss LLMs. So see you next week.